She's totally sick.
Good?
So
No.
sick. I mean, she was in class this morning, so I'm assuming.
Man, if you guys ever just like want to fall asleep on the next day, have a great nap. I'm sick.
Really?
Oh my goodness. I don't know if it's his voice or what. It's just something. Sorry, I have to tell everybody this. I was really struggling today.
And Ian, it's okay. Everybody makes mistakes.
Ian, now.
Everybody has those days.
I'll play it.
Also, this, bro. I was telling you this last night. He doesn't play football.
You think, oh, you're getting covered from playing football? Oh, there might be some truth to that.
The Jackson Browns told me to come down this year.
Still
Okay.
feel like crap, Blake? Still
What's
feel
that?
like crap
There's
from
stuff-
yesterday?
I feel better than yesterday, but the lift this morning kind of worked everything out. So, oh yeah, I was not feeling so high yesterday.
Okay, so today we're picking up with chapter 6, which is the last chapter we cover before the exam, which is in 2 weeks, maybe it's next Friday?
Next Monday.
No, not next Monday.
2 Mondays?
Monday, the next. Not the
Oh,
next-
yeah, no, not next Monday, the Monday after, yeah.
Right, right.
Because it's the day after my birthday.
All right, so
That
everybody
calls
got that?
for
The first exam is the day after Clayton's birthday. I should have put it on their syllabus that way, then we'd all be on the same page.
No, I'll never forget when first.
All right, so, chapter 6 is the last thing we covered before that. So chapter 6, a lot of chapter 6 is actually a review, but it's a review of stuff that maybe wasn't as big an emphasis in statics. Shear and moment diagrams. You guys do shear, remember doing shear and moment diagrams in statics? Okay. So, if I have a cantilevered beam, and it has some distributed load, direction of thought, I drew it. Like that. And let's say there's some kind of a force down here at the end pushing down. Okay? So that's our general condition. If I zoom in on some little piece, some little element of the beam, which has a width of delta x, and this is going to get kind of ugly, this little picture here, so I apologize to those of you watching on video. There's some kind of a load being applied there at the top. And the magnitude of that force is W of x times delta x, or W bar of x actually times delta x. W bar is the average of W of x over that width delta x. All right, so W of x, remember, has units of force per unit length. It's a force density. It's a linear force density. So W of x, force per unit length, times the unit length gives us total force. That same piece will experience a shear force on this side. Right, because, and then there will be a shear force on this side that is slightly more than the piece on the other side. Right, whatever the shear force is, the one on this side is going to be a little bit bigger because it has to, some of the forces has to equal 0. Is this all at least familiar from, okay, so make sure we're reviewing stuff as opposed to teaching stuff. Similarly, there's going to be a moment on this side, M. Should draw these with vectors. And then there's a moment on this side, M plus delta M. Because there's an incremental increase in the moment as we cross from left to right due to the presence of this distributed force. Okay? And for the time being, we're going to pick a point O for our analyses, about which we'll be calculating the moments. Okay, we pick any point, but we're going to pick that point because the math is more straightforward. Okay, so what is delta V? Well, I do sum of the forces, in this case in the y direction. So what are all the forces acting on there? Sum of the forces. V
Minus V. Well, then we have the V going the other direction.
Yeah, it's not V going the other direction. It's not V going the other direction.
Oh, V plus delta V.
Right. Minus V plus delta V. Is that all the forces?
Minus WX times delta X.
Minus?
Plus.
Oh, those arrows are going up. Plus.
Plus W bar of X delta X. And as we assume that the beam is stationary, those have to add to 0. The V and the minus V cancel out, so I'm left with delta V is equal to W bar of X times delta X. Okay. As I let delta X go to 0, as delta X goes to 0, W bar of X just becomes W of X, the value at a particular point. Right? There's no longer an average. And so I get dV dx equals W of X. Okay. And similarly then I get, or I could do Dr. Davis class.
Okay. Oh, so I'm just reading.
So I get the change, if I then take any particular length of the bar, any non-infinitesimal length, then the change in the shear along that length is W of X dx integrated. Okay. So somehow you should be able to remember this piece, that there was an integral. We integrate this function to get our shear. Okay? That makes sense? Everybody remembers that? It all sort of, everybody nods. Do you really remember this stuff? So, you want me to nod? Just a little bit?
I mean, just a little bit.
So still worth going through?
Yes, yes.
Okay.
Yeah,
Okay.
it's,
Well, I don't want to be like boring.
no, it's definitely.
Okay, all right. So then we do the same thing with some of the moments. And again, we're going to do some of the moments about O. So the sum of the moments, what are the moments that exist? What forces exert a moment about O?
The left side shear, and then
Left side shear, okay, so we have V times what's the distance for that? Can we,
delta X.
delta X. V times delta X. All right, is that positive or negative?
Positive. Negative.
Okay, so we'll talk about sign convention in a minute, but it turns out that is positive.
Positive.
Okay,
Yeah.
but yeah. Okay. But we'll talk about the sign convention for moments in a minute. Okay, that's one. What's the next one? What else exerts a moment? Is that it? We have no more moments?
There's no distant, well, I guess the load on top is gonna exert
What's that?
the load on top.
Yeah, W of X, okay. So we have W bar of X, delta X is the force. What's the distance?
X, or X. We have to integrate it to find it,
Yeah, we'd have to find the centroid of that area, right? But that centroid is some fraction, this dimension in here is some fraction of delta X. Right, K is a number between 0 and 1, it's some fraction, we don't care what it is, it's some fraction of delta X, so times K delta X. Okay, that's 2 moments.
And the third one wouldn't act on it because there's no dx, right? It wouldn't have an effect on it. 'Cause it's not like a distance away, so it's got no,
I'm not sure what you mean.
I don't know what I mean.
He's talking about the V.
Oh, the V
Right
plus
side.
delta V, right, so V plus delta V does not create, is not a couple, creating a moment about it.
You would add the 2 moments up.
Right, but you would still add the internal moments.
Yeah.
M and M plus delta M. Okay, is that correct?
No,
What's not correct?
should be a minus sign from the N plus delta M.
Okay, so the M plus delta M should be minus. It's going opposite direction, okay? Right, these are all causing it to turn that way, the M plus delta M is going the other direction. Okay, so we solve that out and we end up with delta M is therefore equal to V delta X plus omega bar of X times K times delta X squared. Right? Okay. So, and K is a number between 0 and 1. Okay, it's just some fraction. As delta X goes to 0, what happens over here? So I allow delta X to get really, really small. What happens to that expression? Not really. Well, look what I have. Look what I did over here. Right? As delta X goes to 0, becomes dx, right? And this becomes dv. So as everything goes to 0, this becomes dm v dx plus omega bar of x k dx squared. Well, that's a little weird, right? It's not really the second derivative, right? That's not a d squared x, that's a dx squared. In fact, that term actually goes to 0. Because dx is a really small number. Then dx squared is going to be an incredibly small number. So in the limit, as delta x goes to 0, I divide this through by delta x, and I get that. And here I've got dm and dx are both small values, so I can keep this one, but that dx goes to 0 because it's too small. That dx goes to 0. So, you remember that from calculus, right? You have a double dx, gets wiped out. Anyway. So, and then, or if I integrate it, represent it in integral form along some length of the bar, delta m is going to be the integral of v dx along that particular length. So, this change in shear as I move along the length is the integral of the area curve, of the load curve. The change in the moment as I move along is the integral of that curve, which is the integral of this one. Right, so the moment is the second integral of this function. Effectively. Okay? One of the things worth noting here is then that the maximum moment occurs when v equals 0. Right? The maximum moment occurred when the derivative of the moment with respect to x is 0. Right? We hit a maximum, right? And the slope is 0, and that slope is defined by the shear. So the maximum moment always occurs when the shear is equal to 0. Okay? So what does that look like? Oh yeah, I didn't do this. I didn't do this other thing too. So that's fine for all these continuous functions. When we have a step function like this, when we have a point load, right, a load applied to a concentrated force, at this location, as we cross from here to here, if there were more beam out there, in this section, delta V is just equal to whatever that applied force is. And if we had a moment applied in there, in other words, there was a couple, well, somebody was twisting the bar here, then delta M would just equal whatever that applied moment was. So we just increment the shear and the moment diagrams to reflect the concentrated application of load or bending moment. Okay? We're all good with that? So the one thing we have left then is the sign convention. And I don't know what sign convention you used last year, because you used a different, you didn't use Hitler. So it can be dependent on the text that you choose. So, if I have a force in the context of Hitler is positive anytime it is upward. Any upward force is positive. And then obviously a downward force is negative. If I have a shear, although this would apply to shear also, well, I'll come back to that, excuse me. A shear is positive if the resulting rotation that it would induce is clockwise. So in this case, the shear that I've applied here is positive because it would cause the sample to rotate clockwise. See what I'm saying? So it's not a right-hand rule thing. Because right-hand rule would say, well, that's into the board. Okay? Instead, it's just a matter of if it will rotate clockwise, then it's considered positive from Hitler's sign convention. Okay, you can choose any sign convention you want. You just have to be consistent with it. But in the context of the problems that you're going to be doing from the homework that are taken from this book, positive is clockwise. And then obviously just negative is counterclockwise. And for moments are a little different. And you would think, well, this moment is also clockwise or counterclockwise. But it turns out the real defining characteristic of the moment is whether it creates compression on the top of the beam or the bottom. So if it creates compression on the top of the beam, it's considered a positive moment. Right, so, or the other way you can look at it is if it's a moment that is causing the beam to cup upward as if it would hold water. Any moment that causes that is considered a positive moment. It takes the beam and causes it to go like this. So you see both of these two cause this beam to come up in that context.
They both do?
Well, in other words, if this was applied at the left end of the beam,
Oh, okay.
and this was applied at the right end of the beam, you see what I'm saying?
So according to Lilith, they're both positive?
So if I applied, this is different, this is the moment, this is an internal moment. What I'm saying is if I applied a moment up here, if I twisted this way, and then I applied a moment down here and twisted it this way, right? Even though the rotation of those two moments are opposite in an absolute sense, they're both causing it to cup in this direction. They're both compressing the top, and so they're both considered to be positively applied moments.
So the internal ones don't follow those rules, though? So you just?
So because if I'm applying a positive moment here,
Mhm.
right, in order to compensate for that, there's an internal moment that
Yeah.
cups it the other way, right? But that still is all one big moment to cup it this
So
way.
when you look at the little piece that you drew,
Right.
those are all positive.
So, no, not really. It's kind of a wonky, it's Hibbler's sign convention. Okay, my sign convention is to use the right-hand rule, because that sort of comes from physics. Right, so any moment that's positive is this moment, any moment that's negative is this moment, okay? In Hibbler's context, it's all about whether it creates a positive curvature or a negative curvature.
So,
I honestly don't know how to,
So it doesn't really matter, you just have to be consistent.
right, exactly. It doesn't make sense to me to do it that way, because I'm so ingrained to the vector notation of moments.
The only thing with homework is you might have a negative instead.
Right, right.
so are,
And on an exam, as long as you're consistent, yeah.
so are those considered?
So these two are opposite moments, okay? But because this is a reaction to that one, I think somehow they are, they're still opposite, but they're, that's what I'm saying. I'm not sure I fully understand
Gotcha.
Hibbler's context of the top being compressed.
Okay.
It makes more sense to me to think of moments in terms of their vector notation at the moment. Okay, so I'm not sure where Hibbler's going with that. I'm just warning you, this is the convention that he lays out
Okay.
in the context of the problems that you guys are going to be solving on homework. They're all from Hibbler. So be aware that this is the sign convention he lays out.
Yeah.
I don't, like I said, that's not my sign convention. My preference is to use vector notation. But you need to be aware of how he's laying things out. Okay. In fact, you can see, as we did this, right? We did, one was positive and one was negative.
Mhm.
Right? That's how we arrived at where we are. So, yeah, I'm not sure where he's going. Any other questions about that? Again, most of this should be stuff that you're familiar with from last year. Again, we're reviewing sort of where it came from, the where it came from piece. But what we really care about is actually arriving at the expressions for B and M. Okay? So any questions before we move on to some problems? Okay. Then let us move on to problem 6.5. A nice, easy softball to start with. Can I erase, Tom?
Yes.
Okay, so for 6.5, it's just asking us to derive the shear and moment diagrams for this beam. So we have the beam. This as a function of x. I'll put some marks in here at 2 meters and another one at 5 meters, because those are the two distinct points in the diagram. Okay? And now, what do we do? Where do we start?
Probably a free body diagram.
Isn't it from body?
I was debating, I just wasn't sure.
Okay, free body diagram of the bar. Okay, what do we got? What am I going to draw?
forces in the moment.
Two forces in a moment, okay? I got a 10 kilonewton force. I've got an 8 kilonewton force. And apparently there's some kind of a moment applied out here, 15 kilonewton meters. Anything else?
Probably reaction force from the wall.
Probably a reaction force from the wall. What's it going to be?
18
Yeah,
kilonewtons.
it's going to be 18 kilonewtons. Don't even have to sum the forces to recognize that, right? No statics involved, really. Just it's pretty straightforward. 18 kilonewtons. That it?
It's also gonna be a reaction moment.
A reaction moment of 15 kilonewton meters. Okay, now we have free body diagram. So, let us begin. Oh, I should draw two of these. Right? I need the V curve and the M curve. And here's 2, and here's 5. All right. Let's do the top one first. What's VE going to look like? What's that?
Up to 18.
Like from the beginning go up to 18?
Makes
Yes?
sense.
Like that? Okay, where do I go from there?
Straight line to 2,
Straight line to 2,
down to 8,
down to 8.
What?
Then do what?
Straight line to 5, down to 0.
All right, pretty easy, right? Pretty straightforward stuff. Okay, what's my M diagram look like? So it's at a negative 15. Why say negative?
Because it's making
Right, right. So it is making it bend downward. See that?
Also, we're gonna use this.
So that you have to know, the reaction, whatever the reaction moment is, that's where you're starting. And it's causing it to bend, it's putting the bottom in compression, so it's a negative 15. Okay?
So, and then we're just gonna assume that the other one's the other sign, even though they're both causing the bottom to compress.
Let's walk it through. I see. We'll walk it through. What did you say?
So if we just watch really carefully, it's different for us.
What do I do next?
Is it a sloping line from 15 to 0 at 5? Because,
From 15 to 0 at 5. I don't know what you mean.
okay, from 15
Uh-huh.
to the 5 tick mark, is there a linear?
There is not a straight line from here to there. What's that?
Is there a straight line from point 0 to negative 15 to 5?
No, there's not a straight line from here to there.
like 0 to
0 to 2.
x-axis.
Okay. So where my line starts here, where's it gonna go? Right to there?
I was gonna go up to positive 36
Up to positive 36?
at 2, this area under the curve. Or area under the. Right? It's gonna go from negative 15, not to positive 36, but it's gonna go up 36 units. So that's gonna be positive 16, right, at 2?
And we still have an issue, actually. I'm waiting for somebody to
The,
address. The what, Caleb?
but, I mean, isn't there something that happens with the 18 something, so when you integrate?
No, there is something wrong with the free body diagram.
Aren't there 2 more moments caused by the 10 and the 8?
Right, exactly. We completely ignored the moments caused by the 8 and the 10.
Mhm.
But if we ignored them, would there be a straight line?
There's a moment caused, these things cause moments, right?
Right.
Yeah.
So we have the 15 applied, plus we have the 8, plus we have the 10, right? This is not 15.
Did
What
you
is
bring
it?
it as well?
What's that?
Did you bring it as well? Or did you just like let us go until we got here?
Well, I was gonna. I was gonna let you try to, you would figure it out when you get down to here, because you add 36 and suddenly we're up to here, and then you add, and you're up to this huge number, and you'd be like, whoa, how could that be? But we weren't actually getting to the adding the things over here very quickly, so I kind of back
That's
this
the
up.
integrating part, right?
Yeah, you got the integrating part, right, yeah, but that was gonna put us way up here, which is nonsense out, okay? So, what should this be?
Plus 20 plus 5, which is 40. So, that's the math.
So the total moments,
Is it 5?
You're just yelling at random numbers, are you?
No.
44.
2 times 10
is
is
75.
22. That's not random numbers.
2 times 10, did you say
75.
2 times 10 is 25?
No, 2 cents 20.
And then
8 times 5 is 4.
Jesse.
alright, just leave the units. So we have moment at A, minus 15, minus
20
20, which is 10 times 2,
minus 40.
minus 40, which is 8 times 5. So MA is 75.
So we were close. We just needed a rule. 7. I needed a 7 in front of it.
So minus 75.
That was rough.
Now then, what do we do next?
So,
Go ahead, I'm sorry, go ahead, Caleb.
and the way you wrote it there with the summation, does that make the negative 75 is
I'm
when
using
you're calling
mine,
negative?
I'm using
Okay, and then the other ones are opposite of them, right?
the other ones are opposite of them, right? So I'm just saying MA is in the opposite direction of all these others.
Gotcha.
So all the ones that equals 0. So
Okay,
it's sort of a vector notation kind of thing.
I just wanted.
But because the top is in tension,
Mhm.
the bottom is in compression, we list that as negative 75,
Yeah.
using the Hilbert convention.
So-
Even though from a right-hand rule standpoint, that's, that applies to them.
So your convention is,
Different
you
than,
do the right hand rule that's pointing towards you, or if you look at other paper,
right,
it points up, points down.
right. So, but again, Hilbert convention, top is in compression.
So now,
So now,
we have a line from 75 to,
mental math.
yeah, you can do it, I just forgot. To the area under the curve, which was 36, I think.
So you're saying a line from the minus 75,
To whatever 75 minus 36 is.
39.
That's what I'm saying.
That's what you're saying. Okay. Then what?
And then another line
Another line,
from negative 39 to negative. Oh, no, yeah, to 40, to positive 1. That's not it.
What?
This is where somebody else jumps in.
Why don't we just follow your summation here?
No, we're letting you have.
so you're saying this as an area of 36. Right? That's what you said? So it's a linear slope because the integration of a constant is a line. And the area is 36, so we added 36. Because this is above.
Oh, it's 3 times 8.
It's 3 times 8, right? So if I add 3 times 8, which is 24, to negative 39, what do I end up with? What was it?
Negative 15.
Negative 15.
What a great guess, Jesse.
15. Right? And then, yeah, you can typically close it off, but anyway. So, and that's right, because we got minus 15 down here. Right? Okay. This is why the compression on the top, compression on the bottom approach works. Right? Because the whole beam is in tension on the top. So the whole beam should have a negative moment, should be experiencing a negative moment. Okay. At this point, I would say this is positive and this is negative in terms of the moment that's applied, if there were an applied moment at that point. That's the distinction between those two approaches. So, okay, but do you understand why we use that convention now? So the whole beam is always in negative. Okay? So, there's our shear and moment diagrams for 6.5, 6-5. Are we ready to tackle the bottom one?
Sure.
All right, let's do 618. Draw the shear and moment diagrams for the beam and determine the shear and moment throughout the beam as a function of x. So in other words, they want a functional expression of the shear and moment, not just a picture. Okay, for the shear and moment diagrams, you're basically looking at the transition points, right? That's what you did. You defined it based on the transition points. Here we're going to end up with some kind of functional equation for those lines or those whatever they are. Okay. All right. So where are we going to start with 618?
Go with free body diagram.
All right. Cantilevered beam again. Uh, 6 feet, right? It's a little past halfway. So here we have downward forces of 6 kips per foot. And then we have one big,
It's
Two kids per foot.
oh, 2 kips per foot, sorry. We have one big 10 kip force there, and then an 8 kip force out here at the end. And then a 40 kip foot moment applied at the end. All right. Let's just do B first, and then we'll draw M. So, is there any other things I need to put in my free body diagram? Or do you want me to change that free body diagram at all?
We have a reacting moment and a reacting force.
Okay, what's the reacting force going to be, upward or downward?
Upward.
And the reacting moment?
Down.
This way. Okay, what's the reacting force?
30.
Kips. I guess 2 kips per foot times 6 feet is 12, plus 10 plus 8 is 30. What is the reacting moment?
It's not 40.
It is not 40. That's correct.
So it's gonna be 13 or 12 times 3, so 10.
12 times what?
Goes halfway.
I just didn't hear you.
Then 10 times 4 and then 8 times 10.
10 times 6.
6.
This is 6 feet. This is 4 feet.
Yeah. 6.
So we'll be able to distribute force, we can
And then
just do like the center of the force,
Centroid.
central.
Centroid of the region, right.
And
So-
then minus 40.
Right, so this, for the purposes of of determining moments or doing the free body diagram, becomes a single force of 12 kips acting at the center of the square. Right, the centroid of a rectangle is right at the center. So we have 12 at 3, 10 at 6, and 8 at 4. That's what Kayla just added up. So how much is that total?
I think it's 216.
Did you get 216, Kayla? You didn't add it up, you were just talking about it.
That is right then.
Okay, so we have 36, plus 60 is 96, plus 72 is 168, plus 40 is 2,
It's 72.
isn't
6 plus 4
8
is
times 12, oh no, 8 times 12 is 86. 8 times 10 is 80.
80, yeah.
216, all right. Whew, okay. Okay, so where does my shear diagram start? Now that I've got my free body diagram done.
Up 30,
What's that?
up 30.
Go up 30. So positive 30. What do I do from there? You know, put my key points in here. That's 6 and 10.
It's going to be a downward slope to
Somebody else want to jump in for Blake? It's a downward slope to,
6, and it's going to be 2 times 6, which is 12, so 12 minus 30, which is 18.
18. So you're saying this.
It's gonna be a downward slope to 18.
Is that what you're saying?
That's what I'm saying.
Do we may agree or disagree with Blake's assessment?
I agree.
You agree?
It's good to me.
Ben agrees. Not quite to a majority because we need 51% to reach majority. Colin, Caleb, Killian.
Well, I agree.
Oh, you agree?
Could we
He's
also,
very quiet about
could we also do like a centroid and do it that way as well?
it. No, you can't do a
You
centroid.
can't do centroid?
No. Because if you did the centroid, it would be 30 until we got to that centroid.
Yeah,
And then it would drop down, and it would drop. So you'd end up with, essentially, if I did it that way, what I would have is I would have a curve, or a thing that looked like this.
Mhm.
So the total area under my curve would be the same, but it's not actually reflective of reality.
Okay.
Okay. Now what do I do from here?
Minus 10, so down to 8, straight down,
Straight down to 8,
all the way over to 10, straight down to 0.
all the way over here, straight down to 0. Everybody okay with that? It's all right? It's all right. I've talked to you guys about this because you had me in class last year. The little guy, the Spanish guy, did a hand puppet.
Oh, yeah.
Here's on the Muppet Show.
He was on the Muppet Show, yeah, yeah. Senor Wences, Senor Wences. Anyway, actually, the guy that said, it's all right, was actually the head in the box, it wasn't the hand puppet, but anyway. Sorry, it's a cultural reference, you guys have no culture, so apparently.
0.
Yeah, all right. All right, that's V. Everybody's happy with V? All right, then what are we gonna do with M? Let's just move that.
Absolutely wrong.
Yeah, right. Try not to let you get too far ahead of yourselves. If you're gonna be wrong, you'd rather be wrong early than late.
True.
Okay, there's
The
M.
airport says-
I've given you a hint, by the way, I've drawn the diagram. Go ahead.
Oh, I was usually around like the airport says when they say make mistakes fast.
Stays fast. That's good. So where do I start?
Or negative,
Negative what?
216.
Negative 216. Yeah, let me draw my 6, and 10. Okay, what do I do now?
I know it ends up at negative 72, just because the area under the shear, but I don't know how it gets there. Parabolic one or the other.
Okay, so you're saying that there's a point here at negative 72, and somehow I have to connect those two dots. Is that what you're saying?
Yeah.
I'm gonna say, because the force is getting larger.
Everybody agree with that or disagree? Anybody have any thoughts?
How do you let integral line?
Wait a second. It's,
Hmm?
When we do the integral line to figure out how it gets there?
Okay, we integrate the function in between to figure out how it gets there. So,
That's just a straight line over. Then it, like the, oh, that's a derivative, never mind.
Retract my draw it as if you were drawing it, so I can draw it, make sure I'm drawing it the way you want me to draw it.
So,
Like that. Are we okay with that?
What effect does the slope have?
One question at a time, Matthew. I have the floor. Is everybody okay with that? See? Ben, I'm assuming you're okay with that since you told me. Now you're not okay with
I
it?
can't decide if it's gonna get up or down.
it's gonna,
Can't you decide between that
Yeah,
and this?
shouldn't it be down because the slope of the line?
because it's a negative slope, so you're gonna be integrating like a negative kx.
Yeah.
Think about it. I'm removing the most moment at the beginning. So it's going to have the biggest change at the beginning and the least amount of change at the end. Now what?
I got a quick question.
Okay.
So, the slope, or the magnitude of the slope is not very big on this function. How does that apply to our curve? It seems to me like,
Well, we're going to do the functional, well, probably not. Like I say, we're going to do a functional description of of the curve in those places as well. But I may just have to give you that functionality because we're going to run out of time. But if this were a steeper slope, then it would be a more, a more extreme curvature. Right? Because the slope and the curvature are related to each other. Okay. Because curvature is the parameter of the second order portion of the quadratic formula, which is the parameter of the first order function in the linear formula, which is the slope. The bigger the slope, the bigger the curvature. Okay. Now what do I do though? From here. Where am I going to end at 10? Going to end at negative 40. How am I going to get there? Straight line. Because the integration of a constant is linear. Right? Does that make sense? 32. Should I change by 32? Is the area of this thing 32? It's 4 wide and 8 high it is.
Oh, isn't it?
So I'm adding 32 to my negative 72 to get to negative 4.
And then to zero.
And then the right will drop up to 0. Okay?
I like how your axis goes like this.
Whatever it takes, okay? Apparently Kayla is a little anal retentive about my axes.
This is fun.
There. Is that better? Okay. Oh yeah, the functional relationship. So, in each of these regions, I need to have a function, right? So in this region, v is equal to 30 minus the slope of this thing is 2x, right? And then up here it's just 8. And the function here then is the integration of that. M is equal to negative x squared plus 30x minus 216. Right, because I'm integrating this with an offset of minus 216. And then here, as I said, here's v is equal to 8. I integrate that. I get m is equal to my starting point of minus 72 plus my, no. That's not right, that's not what they have in here. Interesting. Oh, minus 120, yeah, because I have to extrapolate it back. Right. Right, because x is still defined. So this becomes, instead of minus 72, it becomes minus 120, because that's the actual y-intercept, that line. Okay? All right, next time we'll do some more problems. We've actually covered all the stuff, but the problems get harder, so.
And the test is still scheduled for the 16th.
That test is still scheduled for, has not changed. Yes.
I just
Test
wanna
is
make sure
scheduled for the day after Clayton's birthday. That's how we're all remembering it.
that this